Now let's see the refrigerant for the nuclear demarcation cooling. The refrigerant for demarcation cooling needs to possess the following characteristics. First, the refrigerant should be in metals. Metals have conduction electrons, which allow for faster thermal equilibrium by transferring heat to the nucleus. The metal shows the fast thermal equilibrium between conduction electrons and nuclei due to its short spin lattice relaxation time. The metal has a small Corringer constant due to the short spin lattice relaxation time, which results in a large cooling power and small optimum demarcation field. You can see here the cooling power. If we have small Corringer constant, then we can have large cooling power. And if you have small Corringer constant, the optimum magnetic field becomes smaller. Second, it is preferable to have a large Curie constant, which corresponds to a large number nuclear spin moment lambda n. We can thus have a large cooling capacity and a small ideal optimum demarcation field. You can see here, if we have large lambda n, then we can have large cooling power and large nuclear magnetic moment. Then we can have a smaller optimum magnetization field. Third, at the final demarcation temperature, the metal shouldn't transform into a superconductor. Since the conduction electrons are isolated from other metal elements in the superconducting state, the spin lattice relaxation time increases significantly. As a result, the demarcation process cannot be carried out below the superconductor's critical field. Next, it should be simple to machine process. Also, high purity metal should be available. Next, the internal field needs to be modest. So it's better to have a small internal field. Then the spontaneous ordering temperature is low, so that we may attain low temperature. So if we have a small internal field, then we can have a much lower final temperature. Next, the nuclear spin quantum number should have the value of order 2, and the nucleus should be located inside the cubic structure. So in this case, the electric field would not be position dependent. If these conditions are not met, the nuclear electric quadrupole moment and electric field interact to cause the nuclear dipole moments to align, which prevents further demarcation from taking place. So there's several conditions for better refrigerant for the nuclear demarcation cooling. However, the material that satisfies all of the above requirements cannot be found. There are some conflicting requirements. A rho Kronecker constant indicates a high conduction electron density close to the Fermi level. However, the transition metals that meet this criteria exhibits electronic magnetic and superconducting properties, which goes against the condition for superconductor condition. So it's very hard to find the reference that satisfies all the above requirements, and some of them are conflicting requirements. Okay. Requirement F is not satisfied for materials with high nuclear magnetic moments and large nuclear magnetic moments because they do not have cubic structure. The requirement F is that the material is better to have the cubic structure, but cubic structure, then they have the large magnetic moments and nuclear magnetic moments, high magnetic moments. As a result, it is difficult to find metals that meet the requirements mentioned above. Aluminum, copper, indium, silver, niobium, TL, and PT might be thought of as potential refrigerant materials, but because to their superconducting properties, indium, niobium, or TL has superconducting property. Nuclear electric quadrupole moment, indium, toxicity, limited thermal conductivity, and high cost. These materials are not acceptable alternatives. The majority of those requirements are mostly met by copper, so making it common refrigerant materials for dematerialization cooling. The stable isotopes of copper are copper 63 and copper 65. It has a relatively large Curie constant and nuclear spin quantum number of 0.02. High purity copper is also available for a fair price. It does not possess the superconducting property above 10 microkelvin, but is also easily machine processed. Copper has an internal field of only 0.34 millitesla and a nuclear spontaneous ordering temperature less than 0.1 microkelvin. So as a result, copper is commonly used as a refrigerant in the microkelvin range of temperatures for dematerialization cooling. Hyperfine enhanced nuclear dematerialization refrigeration uses the other refrigerant, the PrNi5. The interaction between nuclear and electronic magnetic dipole is known as hyperfine interaction. In Van Vleck paramagnetic materials, the magnetic field at the nuclei, which is produced by electronic magnetic dipoles, is exceptionally large. Magnetic ions with high Van Vleck susceptibility are present in these materials. In a moderate external field, these ions produce a significant hyperfine magnetic field. This characteristic results from the mixing of these characteristics results from the mixing of wave functions of the excited and the ground states, which results in the formation of high magnetic moments of ions in external field. PrNi5 is the black paramagnetic material that is commonly used. Pr ion constitute the hexagonal structure in this material. Ions produce an induced field in the external field that is k times larger than the applied field at the nuclei. K is 11 times. The ion nuclei are therefore affected by field strength of 1 plus Kb, which is 1 plus K times the applied field B. So about 12 times larger than the applied field. Because of this, 1 plus Kb and 1 plus K lambda n should be used in place of B and lambda n in the equations previously mentioned in the demineralization cooling. With a comparatively high temperature and low magnetic field, Ti equal 25 millikelvin and Bi equal 6 Tesla respectively, this is starting field and the temperature for mineralization process, that we can achieve the entropy reduction of about 70%. The limit temperature and field at this time are approximately 8 millitesla and 9 Tesla, 8 millikelvin and 9 Tesla respectively. There is a maximum, there's a minimum temperature and the maximum field we can use in the laboratory. Using these values, we are only able to reduce the entropy of copper by 10% with these limiting values. But for the PrNi5, we use a little high temperature, 25 millikelvin, and a little low magnetic field for mineralization process, but we can achieve entropy reduction of 70%. The significant Curie constant of PrNi5 represent allows us to have large cooling power per unit of time, unit of volume. So PrNi5 also has a large Curie constant, and so we can have the large cooling power. The high thermal conductivity of the metal nickel plays a role in the benefits of the nuclear demineralization cooling, and the low starting temperature and the field of mineralization process also contribute to the advantage of the electronic demineralization. So this is this PrNi5 is adequate refrigerant for the demineralization cooling. So this high fine enhanced demineralization cooling is therefore commonly used. So for this cooling, we use the PrNi5. However, the high fine interaction causes the internal field of PrNi5 to be a little large, 65 millitesla, and as a result, the achievable temperature is high, 0.19 millikelvin. As a result, this refrigerator is utilized to research the material's physical characteristics in this temperature range, 0.19 millikelvin. Also, this PRN5 uses in the two-stage deionization refrigerator as a pre-cooler. This slide shows table for the refrigerant in the nuclear deionization cooling. So copper is mostly used refrigerant. It has the nuclear spin quantum number 302, and relatively large nuclear magnetic moment, and large Curie constant, and a small cooling constant, and small reaction time, and silver, indium, platinum, Au, indium 2, and PRNI5. So the properties of these materials are given in this table. Platinum is commonly used as the thermometer in the microkelvin temperature range. I will mention this nuclear magnetization thermometer or PT thermometer or in the thermometer parts of the lecture. This slide shows the nuclear demonetization system. There's copper, and you have there's a second stage, and this is first stage, and this dilution refrigerator, and helium 4 part. So here 1 Kelvin, and dilution refrigerator 20 millikelvin, PRNI5 refrigerator 10 millikelvin, and the copper stage temperature is 50 microkelvin. This view shows the size of the nuclear demonstration system. It's about here more than 30 meters, right? Or large size, demonstration system. This figure shows the two-stage nuclear demonstration refrigerator made by a Chile group. First stage is PRNI5 refrigerant, and second stage is copper refrigerant. So the first stage refrigerator PRNI5 was connected to the mixing chamber of the dilution refrigerator through an aluminum heat switch. So this aluminum heat switch and the mixing chamber. So this refrigerant is connected to the mixing chamber through the aluminum heat switch. The copper refrigerant second stage, that's the main stage, was coupled to the first stage by another aluminum heat switch. So this aluminum heat switch, and this is a second stage copper, is connected to the first stage PRN5 through the aluminum heat switch. The first stage's refrigerant was made up of 60 rods of PRNI5 that were 120 millimeter long and 6.4 millimeter in diameter. So 60 rods of this PRNI5 refrigerant is here. 10 mole of refrigerant for the second stage was composed of 96 copper rods with a cross section of 2.2 times 3 millimeter square and the length of 245 millimeter. So this one. After the temperature of mixing chamber reaches 10 millikelvin, so the mixing chamber temperature 10 millikelvin. The first stage is refrigerant PRNI5 was magnetized by 6 Tesla. So 6 Tesla field. Using 6 Tesla field, the PRNI5 is magnetized in the magnetization process. This process results in reduction of 70% of PRNI5's entropy. After subsequent deionization process, PRNI5's temperature reached 0.19 millikelvin. So this. So PRNI5 refrigerant, the temperature, final temperature will be a 0.19 millikelvin. The cooling power of PRNI5 causes temperature of the copper to be reduced to about 3.8 millikelvin. So this cooling power is used to lower the temperature of the copper refrigerant down to 3.8 millikelvin. In the process of magnetization with 8 Tesla field here, the copper's 26% entropy was reduced. After demagnetization, the copper was lowered to its final temperature by reducing the field for 10 hours from 8 Tesla to 10 millitesla. Then the refrigerant achieved its final temperature of 41 microkelvin after a 4-day process of thermal equilibrium. So final temperature you can get 41 microkelvin. So this figure shows the refrigerator's temperature change as a function of time. Temperature change. After 4 days of equilibrium at 41 microkelvin, the temperature continues to be below 50 microkelvin even after 10 days. So the 10 days. So 4 days. After 4 days, temperature reach the lowest temperature 41 microkelvin, and this temperature continues to be below 50 microkelvin even after 10 days. On the 13th day, at this point, so 1 nanowatt of external heat is delivered. So we put 1 nanowatt external input to the refrigerant. Then it is shown that the temperature increase is accelerating. So for a month, the temperature was seen to remain below 0.3 millikelvin. PT and copper NMR thermometers were used to measure the temperature. This apparatus was used to study the specific heat change for diluted helium-3 and helium-4 liquid as function of field. So using this refrigerator, this research was performed.